Most people assume that distance is something you could always, in principle, cross. Given a fast enough ship and enough patience, anywhere could be reached. It is one of the most basic intuitions we have about the universe. And it is wrong. There are places in the cosmos right now that no ship, no signal, no message traveling at the very speed of light could ever reach. Not in a billion years, not in a trillion, not ever. The expansion of the universe has placed them permanently beyond contact. And the boundary that does this, the cosmic event horizon, is not holding still. It is closing in. Galaxy after galaxy is drifting across it in real time, passing out of our reach while we watch, and the sky we know is slowly, certainly, emptying. The expansion of the universe, followed honestly to its end, is not a story about growth at all. It is a story about disappearance, and about a universe that, in the deep future, will have erased the proof that it ever began. Get cozy, subscribe if you haven't yet, because by the end of this, the quiet word expansion will sound like the most final thing you have ever heard. Now, let's slowly settle into this. Part 1. The Universe You Were Taught. There is a picture of the universe that almost everyone carries, and it is a comfortable one. It goes something like this. A very long time ago, around 13.8 billion years ago, everything that exists was packed into an unimaginably hot, unimaginably dense state. Then it began. The universe started expanding, and it has been expanding ever since, growing larger and cooler and more intricate with every passing eon. Stars formed, galaxies assembled, planets cooled and gathered into orbits. And here we are, riding one of those planets, looking out at a sky full of light that has been travelling toward us for billions of years. It is a story of beginnings. It is a story of growth, and almost every part of it is true. When you look up on a clear night, you are looking at the evidence. The faint smudge of the Andromeda galaxy, just visible to the naked eye from a dark enough location, is light that left its source about 2.5 million years ago. The photons entering your eye tonight began their journey before our species existed. And beyond Andromeda, in every direction, lie hundreds of billions of other galaxies, each one a city of hundreds of billions of stars, all of them part of the same expanding whole. We did not always know this. For most of human history, the universe was assumed to be static. Eternal, unchanging. The stars were fixed points on a fixed dome, and they had always been there, and they always would be. Even Albert Einstein, when he first applied his theory of general relativity to the universe as a whole in 1917, found that his own equations predicted a universe that should be either expanding or contracting. He found this so troubling that he added a term to his equations specifically to hold the universe still. He called it the cosmological constant. Years later, he would reportedly describe it as the biggest blunder of his life. We will come back to that term because it turns out to be far more important than even Einstein realized. But for now, hold on to this image. The greatest physicist of the 20th century could not bring himself to believe the universe was anything other than still. The person who changed that was Edwin Hubble. Working at the Mount Wilson Observatory in California in the 1920s, using what was then the largest telescope in the world, Hubble measured the distances to other galaxies and compared them to how those galaxies were moving. He was building on years of patient work by others. Festo Slipher had spent more than a decade, starting around 1912, carefully measuring the light of distant galaxies and noticing that almost all of them appeared shifted toward the red end of the spectrum. Henrietta Leavitt, working at Harvard, had discovered in 1908 a way to measure cosmic distances using a particular kind of pulsing star. Hubble took the redshifts and the distances, put them side by side, and in 1929 he published a short paper with a long title in the Proceedings of the National Academy of Sciences. The paper announced a simple, startling relationship. The farther away a galaxy is, the faster it is moving away from us. That relationship is now called Hubble's law, and it is the foundation of everything that follows in this video. It told us, for the first time, that the universe is not a static stage on which events unfold. The universe is itself an event. It is a process. It is doing something. And here is where the comfortable story usually ends. The universe began, the universe is expanding, and we live inside that expansion. It is a tidy picture, and it is the picture most people keep in their heads for their entire lives. There is nothing wrong with it as far as it goes, but it does not go far enough. It tells you where the universe came from, and it tells you what the universe is doing right now, and then it simply stops. It never asks the next question. It never asks where the expansion is going. It never follows the process forward to see where it leads. That is the question this video is about, not the beginning, the destination. If the universe is expanding, and it has been expanding for 13.8 billion years, then what happens if you keep running that forward? What does the universe look like in 100 billion years? In a trillion? What is the expansion of the universe ultimately for, and what kind of cosmos does it leave behind? The honest answer to that question is one of the most unsettling results in all of modern science. It is not unsettling because it is violent or sudden. It is unsettling for the opposite reason. It is unsettling because it is slow and quiet and gentle and absolutely certain, and because it means the universe you see tonight is a temporary condition. The sky full of galaxies, the faint glow of cosmic history, the very evidence that lets us know the universe had a beginning at all. None of it is permanent. All of it is, slowly, on a schedule we can partly calculate, going away. The story of cosmic expansion, told honestly and told all the way to the end, is not a story of growth. It is a story of disappearance. And to understand why, we have to start by taking the comfortable picture you have been carrying and gently, carefully taking it apart. Because the first thing you think you know about the expanding universe is not quite right. There is a detail in Hubble's discovery worth lingering on, because it tells you something about how slowly even an obvious truth can arrive. The galaxies were not new objects. People had been looking at them for centuries. Faint smudges of light that astronomers catalogued as nebulae, from a Latin word meaning cloud. For a long time, nobody was even sure what they were. Some thought they were clouds of gas inside our own Milky Way. It was not until the 1920s that Hubble, measuring the distance to the Andromeda Nebula, proved that it was not a cloud inside our galaxy at all. It was a separate galaxy, a whole other island of hundreds of billions of stars, impossibly far away. In a single measurement, the known universe became thousands of times larger than anyone had imagined. And then, only a few years later, that same astronomer showed that all of those newly discovered island galaxies were rushing apart. In the span of a single decade, the universe went from a modest, static collection of stars to an enormous, expanding cosmos of galaxies. It is one of the fastest and most complete revolutions in the history of human understanding. And yet, notice what that revolution did not include. It told us the universe was vast, and it told us the universe was expanding. It did not tell us what the expansion meant for the future. Hubble measured the law. He did not follow it forward. That next step, the step from describing the present to forecasting the destiny, would take physicists most of the rest of the 20th century. And the answer they would eventually arrive at is the answer that this video exists to explain. The comfortable picture, the one almost everyone carries, froze in place right after Hubble. It absorbed the expansion and then stopped. It never asked the harder question. I want to be clear about why that harder question matters, and why it is worth 2 hours of a quiet night to think about. It is not because the deep future is a practical concern. Nothing we are going to describe affects your life, or your children's lives, or the lives of any human generation we could meaningfully imagine. The timescales are simply too vast. This is not a warning in the way that word is usually meant. It is something different. It is a chance to see the universe whole, to see not just the snapshot we happen to live inside, but the entire arc, beginning to end, and to understand our own moment by its place in that arc. There is a particular kind of clarity that comes from knowing where you are in a story. And the story of cosmic expansion, it turns out, has placed us somewhere very specific, and somewhere, in its own quiet way, rather remarkable. Part 2. Expansion is not what you picture. When most people imagine the expanding universe, they picture an explosion. There was a big bang after all, and bangs are explosions, and explosions throw debris outward into the space around them. So the mental image is something like a grenade going off in an empty room. The galaxies are the fragments, hurtling away from some central point, flying out through a pre-existing emptiness. It is a vivid image. It is also wrong, and the way in which it is wrong matters enormously for everything that comes later. So let us take a moment, slowly, to replace it. In an ordinary explosion, the debris moves through space. The room was already there. The air was already there. The fragments travel through that pre-existing arena, getting farther apart because each piece is moving. That is not what the expansion of the universe is. The expansion of the universe is not galaxies moving through space. It is space itself stretching. This is a difficult idea, so let us build it carefully. Imagine a vast grid, like a sheet of graph paper that extends in every direction without end. Now place a galaxy at some of the intersections of that grid. Not all of them, just here and there, scattered across the grid like raisins in a loaf of bread before it goes in the oven. Each galaxy sits on its own intersection, and it stays there. The galaxies are not crawling across the grid. They are parked. Now, instead of moving the galaxies, stretch the grid. Let every line of the graph paper lengthen, so that the squares of the grid grow larger everywhere, all at once. The galaxies do not move. They stay exactly where they are, each one parked on its own intersection. But because the grid itself is growing, the distance between any two galaxies increases anyway. Watch any single galaxy from any other, and it appears to recede. Nothing travelled, nothing was thrown, and yet everything is getting farther apart. That is the expansion of the universe. The galaxies are the raisins. Space is the dough. And when the dough rises, every raisin moves away from every other raisin. Not because the raisins are swimming through the dough, but because there is steadily more dough between them. This picture explains something that the explosion picture cannot. In the explosion picture, there has to be a center, a place where the grenade went off, and the galaxies should be flying away from that special point. But that is not what we observe. We observe every galaxy receding from us, in every direction, with the more distant ones receding faster. And here is the thing that surprises people. An observer in any other galaxy, anywhere in the universe, sees exactly the same thing. They see everything receding from them, too. There is no center, there is no edge, there is no special location that the expansion is happening around. The dough is rising everywhere, so every raisin has equal claim to being the one standing still while the others flee. Now, this rising dough picture also resolves something that bothers almost everyone the first time they hear about cosmic expansion. We know there is a cosmic speed limit. Nothing can move through space faster than light. So how can the universe be billions of light years across? And how can distant galaxies be receding from us at tremendous speeds without something breaking that rule? The answer is that the speed limit applies to things moving through space. It does not apply to the stretching of space itself. A galaxy, sitting on its grid intersection, is not moving through space at all. It is at rest, locally. But the space between it and us is expanding, and if there is enough space between us, the total amount of stretching can add up to a recession faster than light. There is no rule against that, because nothing is actually traveling. The galaxy is parked. The grid is growing. In fact, this is happening right now. There are galaxies we can see tonight, galaxies whose light is arriving in our telescopes that are currently receding from us faster than the speed of light because of the cumulative stretching of all the space between us and them. The most distant confirmed galaxy we have ever observed, a faint object catalogued as Jade's GZ14, whose light left it only about 290 million years after the Big Bang, is at this moment racing away from us at roughly twice the speed of light. Its light still reaches us, because that light was emitted long ago, when the galaxy was much closer. But the galaxy itself, today, is receding faster than any signal could ever travel. Sit with that for a moment, because it is the first genuine crack in the comfortable picture. The universe is not what it appears to be. What looks like a simple scene of objects scattered through space is actually a sheet of space that is itself in motion, stretching, growing, carrying its contents apart, not by pushing them, but by inflating the very gaps between them. And once you accept that, once you really understand that expansion is the growth of space rather than the motion of galaxies, a question naturally follows. If space is stretching, what happens to the things inside it over a very long time? We have established what the universe is doing. The next question is the one that turns this from a curiosity into something far more serious. What happens next? Let us slow down and really inhabit the grid for a moment, because this is the single most important image in the video, and it is worth feeling rather than just hearing. Close your eyes if you are not driving or doing anything that needs them, and build the picture inside your mind. You are looking at an enormous lattice, a three-dimensional grid of fine glowing lines, extending away from you in every direction with no edge anywhere. At certain crossing points of the lattice, there are galaxies. Picture them as small, bright knots of light, resting on the intersections, motionless. They are not drifting, they are not flying. Each one simply sits on its node, exactly where it belongs. Now, hold the galaxies fixed in your attention and watch only the lattice. The glowing lines begin, very slowly, to lengthen. Not snapping, not jerking, just a smooth, patient elongation, every segment of every line growing at the same gentle rate, everywhere at once. The grid is swelling. And because the grid is swelling, the knots of light, though not one of them has moved from its node, are slowly drawing apart from one another. A galaxy 2 nodes away from you separates from you at a certain rate. A galaxy 10 nodes away separates 10 times faster, because there are 10 lengthening segments between you and it instead of one, and all 10 are growing together. That, exactly that, is Hubble's law. The farther away, the faster the recession, not because distant galaxies move faster, but because there is more stretching lattice piled up between you and them. Feel the difference between the two pictures. In the explosion picture, there is effort. The galaxies are flung, they have velocity, they push through space. In the grid picture, there is no effort anywhere. Nothing is flung, nothing pushes. Every galaxy is perfectly at rest on its own node, doing nothing at all, and the separation happens regardless, carried entirely by the swelling of the space between. The expansion of the universe is not a thing the galaxies are doing. It is a thing that is being done to the space they sit in. The galaxies are passengers. The grid is the story. Once you hold that image cleanly, a great many confusing things become simple. There is no center, because there is no special node. Every intersection of an infinite lattice is exactly like every other. There is no edge, because the lattice has no boundary. And there is no outside, no surrounding emptiness the universe is expanding into, because the grid is not sitting inside a larger room. The grid is everything there is. It is not expanding into space. It is space, and it is expanding. The question, what is it expanding into, has no answer because it contains a hidden, false assumption. The assumption that the grid needs somewhere to go. It does not. It simply grows internally, every segment lengthening, and that internal growth is the whole of what we mean by the expansion of the universe. Part 3. The turn nobody expected. For most of the 20th century, cosmologists were fairly confident. They knew how the story of expansion would end. They did not know all the details, but they thought they understood the basic plot, and the basic plot came down to a contest between two things. On one side was the expansion itself, the outward stretching of space, set in motion in the earliest moments of the universe. On the other side was gravity. Every galaxy, every star, every atom in the universe pulls on every other one. Gravity is always attractive. It always works to pull things together. So the cosmos was understood as a kind of tug of war. The expansion was flinging everything apart, and gravity was patiently, relentlessly trying to pull it all back. The question was simply which side would win. If there was enough matter in the universe, gravity would eventually overcome the expansion. The outward rush would slow, stop, and reverse, and the universe would collapse back together in a kind of mirror image of the Big Bang, sometimes called the Big Crunch. If there was not quite enough matter, the expansion would win, and the universe would coast outward forever, slowing down all the while, but never quite stopping. And if the amount of matter were perfectly balanced on the knife's edge between those two outcomes, the universe would expand forever, but ever more slowly, approaching a standstill it would never quite reach. Notice what every single one of those scenarios has in common. In all of them, the expansion is slowing down. That was the one thing nobody questioned. Gravity pulls inward. Gravity is the only long-range force that matters on cosmic scales. And so the expansion, whatever else it did, had to be decelerating. The only real question was how much. In the 1990s, two independent teams of astronomers set out to measure exactly that. They wanted to measure the deceleration of the universe, to pin down how quickly the expansion was slowing and therefore which of the possible fates awaited us. One team was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams used the same basic tool, a particular kind of stellar explosion called a Type 1, a supernova. A Type 1, a supernova, is extraordinarily useful because it is, to a very good approximation, a standard candle. These explosions all detonate with very nearly the same intrinsic brightness. That means if you see one and it looks faint, you can work out how far away it must be because you know how bright it truly is, and you can measure how bright it appears. And by also measuring the redshift of its light, you can work out how much the universe has expanded since that light was emitted. Distant supernovae are, in effect, mile markers scattered across cosmic history. Both teams expected the same result. They expected to find that distant supernovae whose light was emitted long ago would show the signature of a universe that used to expand faster than it does now. They expected deceleration, and in 1998, both teams, working separately, checking each other, looking for any mistake they could find, announced the same astonishing conclusion. The expansion of the universe is not slowing down. It is speeding up. The distant supernovae were fainter than they should have been. They were farther away than a decelerating universe could account for. The only way to make the numbers work was to accept that, several billion years ago, the expansion of the universe stopped slowing and began to accelerate. Something had switched the cosmos from coasting to accelerating, and that something was actively pushing space apart, harder and harder as time went on. This was not a small adjustment to the picture. It overturned the entire expected ending. There was no longer a simple tug of war between expansion and gravity, because something was now winning on behalf of the expansion, something that did not pull inward like gravity but pushed outward, and pushed harder the more space there was for it to act in. The discovery was so significant and so thoroughly confirmed in the years that followed that Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. But naming the discovery did not explain it. Physicists needed a term for whatever this outward-pushing thing was, and the term they settled on was dark energy. It is important to be honest about what that name means. It does not mean we understand it. The word dark, here, is a confession. It is a label for our ignorance. Dark energy is the placeholder name for whatever is causing the expansion of the universe to accelerate. And more than 25 years after its discovery, we still do not know what it is. What we do know is how much of it there is, and the amount is staggering. When you add up everything in the universe, all the energy and all the matter, dark energy accounts for roughly 68% of the total. Dark matter, itself a mystery, accounts for about another 27%. And everything else, every star, every planet, every cloud of gas, every living thing, every atom that has ever been touched or seen or studied, all the ordinary matter in existence, comes to less than 5% of the universe. Let that ratio settle for a moment, because it reframes our whole situation. The universe is dominated, overwhelmingly, by something we cannot identify. The ordinary matter that makes up everything familiar is a thin froth on the surface of a cosmos whose main ingredient is a mystery. And that mystery is not passive, it is doing something. It is the engine of the accelerating expansion. It is the force that has taken over the fate of the universe. So the comfortable picture has now cracked twice. First, we learned that expansion is the stretching of space, not the motion of galaxies. Now we have learned that this stretching is not coasting gently toward a standstill. It is accelerating, driven by an unknown thing that makes up most of reality. And an accelerating expansion does not lead to the same place a coasting one would. It leads somewhere very specific, and to see where, we need to look at a boundary that most people have never heard of, and that quietly governs the entire future of everything we can see. It is worth pausing on how genuinely shocking the 1998 result was to the people who found it, because the discovery of cosmic acceleration is not a story of scientists confirming what they hoped. It is a story of scientists confirming what they dreaded. Both teams went into the work expecting deceleration. Their instruments, their analysis pipelines, their entire mental framework were built around measuring how much the expansion was slowing. When the first results came in suggesting the opposite, the immediate reaction was not triumph. It was suspicion. The scientists assumed they had made a mistake. They checked their work. They looked for errors in the supernova brightness calibrations, in the dust that might be dimming distant light, in every assumption that could possibly be wrong. Adam Rees has described going through the analysis again and again, trying to find the flaw, because the answer the data kept giving was an answer that, in his words, nobody was looking for and nobody wanted. And the other team, working completely independently, with different software and different people, was going through the same uncomfortable process and arriving at the same uncomfortable place. That is, in fact, the strongest possible kind of scientific result. A discovery that the discoverers actively tried to make go away, that survived every attempt to kill it, that two rival teams confirmed against their own expectations. When that happens, you are not looking at wishful thinking or at a fashionable theory. You are looking at the universe refusing to be talked out of something. The acceleration was real. The teams could not make it disappear, and so, reluctantly, they announced it. And consider what they were actually announcing. Not a new planet, not a new kind of star, not a refinement of a known number. They were announcing that the dominant force shaping the future of the universe was something that had never been observed, never been predicted with any confidence, and had no place in the established inventory of physics. They had found, by accident, while looking for something else, the largest single component of reality. Imagine surveying a house you thought you knew well, and discovering that 2/3 of it consists of rooms you had never noticed, rooms you cannot enter, rooms whose purpose you cannot determine, and then realizing that those unknown rooms are slowly pushing the walls of the house apart. That is roughly the situation cosmology found itself in after 1998, and it is, remarkably, still the situation today. There is a humility in that which the channel wants to honor. We are going to spend the rest of this video describing the fate of the universe with what may sound like confidence, the 100 billion years, the empty sky, the isolated island, and all of that genuinely does follow from the evidence. But underneath every confident sentence sits this fact, that the engine of the whole process was a complete surprise, that we did not see it coming, and that the most honest thing a cosmologist can tell you about dark energy is still, after a quarter of a century, that we named it so we would have something to call the thing we cannot explain. Part 4. The horizon that hides things. To understand where an accelerating universe is headed, you have to understand a particular boundary, and the first thing to say about this boundary is that it is not science fiction and it is not a metaphor. It is a real feature of the universe. It has a measurable size, and it is the single most important concept in this entire video. It is called the cosmic event horizon. Let us build up to it gently, because the idea is subtle and it deserves patience. Start with an ordinary horizon, the kind you see standing on a beach, looking out at the ocean. That horizon is a limit on what you can see, created by the curve of the Earth. A ship beyond it is hidden from you. But notice something about that ordinary horizon. It is not a wall. The ship is not trapped. If you got in a boat and sailed toward it, the horizon would recede ahead of you, and the hidden ship would come into view. An ordinary horizon hides things, but it does not hide them permanently. It is a limit you can overcome by moving. The cosmic event horizon is a horizon of a different and far stranger kind. It is a limit on what can ever reach you, and unlike the horizon on the beach, you cannot overcome it by moving, and neither can anything else, ever, by any means. Here is where it comes from. Light is fast, but it is not infinitely fast. When a distant galaxy emits a beam of light toward us, that light begins a long journey across the space between us. But remember what we established earlier. That space is not sitting still. It is expanding. So the light is, in a sense, swimming upstream. It is trying to cross a distance that is itself growing while the light crosses it. If the expansion were gentle enough, the light would still make it. It would lose ground to the stretching, but slowly enough that it would eventually arrive. But the expansion is not merely happening. It is accelerating. Dark energy is pushing space apart harder and harder as time goes on. And that changes everything, because it means that for galaxies far enough away, the space between us and them is being created faster than light can cross it, and the gap will keep widening faster forever. For those galaxies, a beam of light aimed straight at us will never arrive. Not because it slows down, not because it stops. It travels at the full speed of light, the whole way, and it still never reaches us, because the road it is traveling on lengthens ahead of it, faster than the light can advance. The light swims as hard as it can, upstream forever, and the shore gets farther away the whole time. The cosmic event horizon is the dividing line between the galaxies whose light can still reach us and the galaxies whose light never will. It is not a physical object. There is nothing there to see. It is a boundary defined entirely by the relationship between the speed of light and the rate of cosmic expansion. And under our best current model of the universe, That boundary sits at a proper distance of about 16.5 billion light-years from us. Any galaxy currently beyond that distance is already, in the most complete sense of the word, unreachable. Not unreachable with present technology, not unreachable for now, unreachable, full stop, forever. We could build a ship that travels at the very speed of light, launch it today, aim it perfectly, and it would never arrive. We could send a radio signal, the most patient message imaginable, and wait not 1 billion years but 1 trillion, and it would never get there. The accelerating expansion has placed those galaxies permanently outside our reach. The connection has been cut. Now, there is a subtlety here that is genuinely important, and it is one that even popular accounts of cosmology often blur. So let us take it slowly and get it right. You may have heard that there is a distance at which galaxies recede from us at the speed of light, and you might assume that distance is the same as the event horizon. It is not. The distance at which the pure recession velocity equals the speed of light is called the Hubble sphere, and it sits at about 14.4 billion light-years, somewhat closer than the event horizon. And here is the subtle part. A galaxy can be beyond the Hubble sphere, receding from us faster than light, and its light can still, eventually, reach us. That sounds like a contradiction, but it is not. Think again about the light swimming upstream. Even if the galaxy is receding faster than light when the light sets out, the photon can drift outward into regions of space where, relative to us, the expansion is a little slower. As the universe evolves, the Hubble sphere itself can grow, and a photon that started outside it can find itself, later, inside it, and from there it can complete the journey home. So, the Hubble sphere is not a true point of no return. Light from beyond it can still arrive. The cosmic event horizon is the true point of no return. It accounts for the entire future history of expansion, not just the rate today. It is the honest boundary, the one that answers the real question, which is not how fast is that galaxy receding right now, but rather, can any signal it sends ever, under any circumstances, reach us? If the galaxy is beyond the event horizon, the answer is no, and the answer will always be no. There is one more property of this horizon that we need, and it is the property that turns this video from an explanation into a warning. Under an accelerating expansion, the cosmic event horizon does not stay put. Measured in the coordinates that track real galaxies, it shrinks. It draws inward over time. The region of the universe that remains in contact with us gets smaller. And that means galaxies are not safely on one side of the horizon or the other. They are crossing it, right now, in real time. One after another, galaxies that are currently within our reach are drifting toward that boundary, and when they cross it, they pass out of our future forever. They do not vanish from the sky when they cross. This is the strange and quiet part. Their old light, emitted before the crossing, keeps arriving for a long time afterward, slowly reddening and dimming. So we go on seeing them, like a photograph of someone who has already left the room. But everything they do after the crossing, every event in their entire future, is lost to us. We will never see it. We can never be affected by it. The galaxy and everything in it has been moved gently and permanently out of our universe. That is the horizon that hides things. And the truly disturbing truth of cosmic expansion is what happens when you let this process run, not for a year, not for 1 million years, but for the long, deep stretches of cosmic time. Because if galaxies are crossing the horizon one by one, then there is a question that answers itself with terrible simplicity. What happens when they have all crossed? Let us stand with this horizon for a while, because it rewards slow attention, and because the difference between an ordinary distance and a horizon distance is the difference between being far away and being gone. Picture a wide, flat plain at dusk. The light is failing, gently, the way it does on a long summer evening. Far out across the plain, a figure is walking away from you, unhurried, growing slowly smaller. You can see them perfectly well. There is nothing dramatic happening. They are simply walking, and the plane is wide, and the light is going. Now, on an ordinary plane, you could always close that distance. You could walk faster or run and catch them, because the ground between you is fixed. The figure is far away, but far away is a temporary condition, a condition you can change with effort and time. That is what distance normally means to us. It means a gap that, in principle, could be crossed. But imagine the plane itself is slowly stretching. Imagine the ground between you and the walking figure is lengthening, gently, everywhere, and lengthening faster the more of it there is. Now run toward them. You run as hard as you can, full speed, the fastest anything can possibly go, and the gap does not close. The stretching of the ground feeds new distance into the space between you faster than your running can eat it. You will run forever, at full speed, and never gain a step. The figure is not walking away from you especially fast. They may barely be moving at all. It is the ground that has defeated you. That is a horizon. And the figure who walks beyond it has not died, and has not vanished, and is not, in any local sense, even very far away by cosmic standards. They have simply become permanently uncatchable. The gap between you has changed from the ordinary kind, the kind that effort can close, into a different kind, a kind that nothing can close, ever, by any means. The figure is still out there. They are simply, now, in a part of reality you can never again touch, and never again be touched by. When a galaxy crosses our cosmic event horizon, that is exactly what has happened, not destruction, not disappearance. A change in the category of the distance. Before the crossing, that galaxy and ours were part of a single connected reality, two places between which a signal could in principle pass. After the crossing, they are two separate realities that happen to lie in the same dark, forever sealed off from one another. The light already in transit still arrives, for a while, like a letter posted before the sender moved away to an address that no longer receives mail. But no new letter can ever follow it. The correspondence is over. And the universe has many, many such correspondences, and it is, quietly and continuously, closing them. Part 5. One by one, the lights go out. In 2007, two physicists, Lawrence Krauss and Robert Scherer, published a paper that followed the logic of accelerating expansion to its conclusion and described, in careful detail, what the universe will look like in the deep future. The paper had a title that did not flinch. It was called The Return of a Static Universe and The End of Cosmology. And what it described is the quiet center of this entire video. To understand it, picture the universe as it is arranged tonight. We live in the Milky Way, an enormous spiral of several 100 billion stars. The Milky Way is not alone. It belongs to a small cluster of galaxies gravitationally bound together called the local group. The local group contains the Milky Way, the slightly larger Andromeda galaxy, the smaller Triangulum galaxy, and several dozen dwarf galaxies orbiting among them. That is our cosmic neighborhood, our home cluster. And beyond the local group lies everything else: the Virgo cluster, the Coma cluster, the vast cosmic web of galaxies and filaments and voids stretching out in every direction, hundreds of billions of galaxies, the whole observable universe, all of it, right now, visible, all of it, right now, woven into the same sky we can study. Now let the accelerating expansion run forward. Every galaxy that is not gravitationally bound to our local group is being carried away by the stretching of space, and the acceleration means each one is receding faster as time goes on. Each of those galaxies is drifting slowly toward our cosmic event horizon, and one by one, Over the coming tens and hundreds of billions of years, they will reach it and cross it and pass out of our reach forever. Krauss and Scherer put a number on it. In roughly 100 billion years, every galaxy outside our own local group will have crossed the cosmic event horizon. The entire rest of the universe, the hundreds of billions of other galaxies, will have receded beyond the boundary from which any signal can ever return. The extragalactic sky, the sky beyond our own merged galaxy, will be empty. Let us slow down and stand inside that, because a number that large does not land unless you let yourself feel it. Imagine you are standing on a world somewhere near the edge of the local group, far in the future, with the ability to watch the sky in time-lapse 100 billion years compressed into a single, slow evening. At the start of that evening, the sky is as rich as ours, scattered with the faint glow of countless distant galaxies, each one a smudge of light, a city of stars. It looks like the night sky of a settled universe, full and busy and connected. Then, as your long evening wears on, the smudges begin to change. The most distant ones go first. They redden because their light is being stretched ever further toward the dim end of the spectrum as the space it crosses expands. They fade because the photons arrive more and more slowly and more weakly, and then, one by one, they wink out, not in a flash, not with any drama. They simply grow too faint, too red, too slow, and they are gone. It is like standing on a hillside at dusk and watching a wide valley full of houses, each with a lit window, and seeing those windows go dark, one at a time, scattered across the valley, with no pattern and no sound. A light here, a light there, the valley slowly emptying of light. And you cannot call out to any of those houses, and you cannot walk to them, and you know, watching, that each window that goes dark is one you will never see lit again. By the end of your long evening, 100 billion years in, the valley is black. Every window has gone out. The sky beyond your own galaxy holds nothing at all. No other galaxies, no distant light, just your own stars, and then, past them, perfect and featureless dark. This is not a catastrophe in the way we usually picture cosmic doom. Nothing exploded. Nothing was destroyed. Those galaxies still exist, out there, full of their own stars and presumably their own histories. They have not died. They have simply been carried beyond the horizon, beyond all possible contact, by the patient stretching of space. From our side of the horizon, the effect is the same as if they had never existed at all. The universe will not have ended. It will have become unreachable, almost entirely, leaving us alone with our own small island of light in an ocean of dark. And that word, alone, is the one that should give us pause, because it raises an obvious and uncomfortable question. If everything beyond the local group is being carried away, then what about the local group itself? What about the Milky Way? What about the ground under your feet? If space is expanding everywhere, and expansion carries things apart, then is everything being pulled apart, all the way down? Are we, too, being slowly stretched toward dissolution? The answer to that question is genuinely surprising, and it is the key that unlocks the second half of this story, because the expansion of the universe, it turns out, does not touch everything. It is far more selective than that. It helps, when a number like 100 billion years is on the table, to put it against numbers we can almost feel, because otherwise it is just a word. The universe right now is about 13.8 billion years old. 100 billion years is more than 7 times that. So the era when the extragalactic sky finishes going dark is not a near edge of the future. It is deep, deep out, more than 7 full lifetimes of the universe, so far away from tonight. If you compressed the entire history of the universe up to this moment into a single year, with the Big Bang on the 1st of January, and right now at the last midnight of December, then the emptying of the sky would not happen until somewhere around the middle of the 8th year of that calendar, We are, by that reckoning, still extremely early. The dark era is real, and it is coming, but it is coming with a slowness that ought to be part of how we feel about it. Nothing about this is sudden. Nothing about this is a threat in the ordinary sense. It is the most patient process imaginable. And yet patience does not make it less final. This is the strange emotional texture of the deep future, and the script wants to sit inside that texture rather than rush past it. The emptying of the sky is gentle and slow and completely unstoppable, all at the same time. There is no force we could imagine, no technology, no civilization, however advanced, that could reach out and hold the receding galaxies in place. They are not being pushed by anything that could be switched off. They are being carried by the expansion of space itself. And the expansion of space is not a mechanism with an off switch. It is the behavior of reality. To stop the sky from emptying, you would have to stop the universe from being the kind of universe it is. So return to the hillside above the valley and watch a little longer. We said the windows go dark, one by one, scattered, without pattern. Let us be precise about the order, because there is an order. The most distant galaxies cross the horizon first, because they were already receding fastest, so the faintest, farthest smudges of light are the first to redden into nothing. Then the next nearest. Then the next. The darkness does not fall everywhere at once. It closes inward, like a tide coming up a beach, the far water going first, and the boundary of dark creeping steadily nearer, until only the closest galaxies are left, and then they too redden and slow and are gone, and the tide of dark has come all the way in. When it is finished, the survivor, our own merged galaxy, sits inside a perfectly black extragalactic sky. And here is the part to carry into the next stretch of the video. That blackness is not empty in the sense of being a void where galaxies used to be and have been destroyed. The galaxies are all still out there, every one of them, shining, turning, carrying on. The blackness is the blackness of disconnection. It is the dark of a phone line that still has someone on the other end, someone alive and well and talking, whose voice simply can no longer reach the receiver. The deep future is not a dead universe. It is a universe full of life and light, every island lit, and not one island able to see another. That is a far lonelier picture than mere emptiness, and it is the true one. Part 6. Why you are not expanding. Here is one of the most natural questions anyone can ask about the expanding universe, and it is a good one. If space itself is expanding, everywhere, all the time, then why is it not expanding here? Why are you not slowly growing? Why is the Earth not gradually inflating? The distance from here to the Sun not quietly lengthening? The Milky Way not stretching apart at the seams? If the dough is rising, why are the raisins not rising too? The answer reveals something essential about what cosmic expansion actually is, and it is the secret that explains why the deep future is the particular kind of future it is. Expansion does not stretch everything. It stretches the gaps between things that are not bound together. And almost nothing you can see or touch falls into that category. Think again about the rising dough with the raisins in it. We said, the raisins move apart as the dough rises. That is true for raisins sitting freely in the dough, with nothing connecting them. But now imagine that two of those raisins are not free. Imagine they are glued together, joined by a strong, stiff bond. As the dough rises around them, what happens to that glued pair? The dough between them tries to push them apart, but the glue holds. The bond is far stronger than the gentle outward pressure of the rising dough, and so the glued raisins stay exactly the same distance apart, even as the dough swells around them. The expansion is still happening. It simply cannot win against the bond. That is your situation. That is the situation of everything you have ever known. The atoms in your body are held together by electromagnetic forces, and those forces are stupendously stronger than the tendency of cosmic space to expand. The expansion does not stand a chance against the bonds in a single molecule. So your body does not grow. Not at all. Not even slightly. The Earth is held together by gravity and by the electromagnetic bonds of solid rock. It is not expanding. The Earth's orbit around the Sun is held in place by the Sun's gravity, an enormous, dominating force at that scale, and the orbit is not slowly widening. The solar system is bound. It is not expanding. The Milky Way galaxy, several 100 billion stars wheeling around a common center, is held together by the gravity of all that matter, plus a great deal of dark matter. It is bound. It is not expanding. And the local group, our cluster of galaxies, the Milky Way and Andromeda and Triangulum, and all the dwarfs, is gravitationally bound as a unit. The local group is not expanding either. Cosmic expansion only wins, only actually carries things apart, in the vast, nearly empty spaces between galaxy clusters, where matter is so thinly spread that gravity's grip is weak and there is nothing strong enough to resist the steady stretching of space. Out there, in the great voids, expansion runs unopposed. But inside any island of matter that gravity or electromagnetism has bound together, expansion is overruled. The bond wins, the island holds. This is why your body is not slowly inflating, and it is also why the deep future is the shape it is. Run the picture forward. The expansion will keep carrying the distant, unbound galaxies away, widening the empty voids without limit. But it will never pull apart the things that are bound. The bound islands survive. Every gravitationally bound structure rides out the expansion completely intact, while the gulfs between those structures grow without end. So picture the deep future correctly now. It is not a universe being torn to shreds. It is a universe of intact islands, each one whole and undisturbed, drifting ever farther from every other island, until the distance between them is so great and growing so fast that no island can ever again signal another. The expansion does not destroy the islands. It isolates them. It is a process not of dissolution but of separation. The universe does not come apart. It comes apart only at the seams between its bound pieces, and those seams are precisely the empty places where nothing lives. There is something almost merciful in that, at first hearing. Your galaxy is safe. Your cosmic neighborhood is safe. The expansion cannot reach into the local group and undo it. We are not headed for a future in which the Milky Way is ripped apart, but hold that sense of relief lightly, because it does not survive close inspection. Yes, our island is safe. The trouble is, what safety means when the entire rest of the universe has been carried beyond the horizon. To be a bound, intact, surviving island is to be the one house on the hillside with its lights still on after every other window in the valley has gone dark and after the valley itself has drifted so far away that no road could ever reach it again. Survival in the deep future is not the same thing as company, and that distinction is where this story turns from a description of physics into something that genuinely unsettles. It is worth being precise about just how lopsided this contest between expansion and binding really is, because the numbers involved are not close. People sometimes imagine that expansion is a force quietly tugging at everything, winning slowly against the things that hold matter together, and that bound systems survive only by a narrow margin. That is not the situation at all. The margin is not narrow. It is astronomical in the most literal sense. Consider the bond between two atoms in a molecule in your hand. That bond is electromagnetic, and on the scale of a molecule, the electromagnetic force is overwhelmingly, crushingly dominant. The tendency of cosmic space to expand, evaluated at the scale of a molecule, is so much weaker that the comparison is almost meaningless. It is not a tug of war that the molecule is winning by an inch. It is a tug of war in which one side is an ocean liner and the other side is a single bacterium pulling on a thread. The molecule does not notice the expansion. It cannot notice it. The expansion, at that scale, is not a small effect. It is a no effect. The same lopsidedness holds, with room to spare, at the scale of the Earth and the solar system and the galaxy. The Sun holds its planets with a gravitational grip vastly stronger than anything expansion could bring to bear across the width of a planetary system. The Milky Way holds its hundreds of billions of stars and its great reservoir of dark matter in a gravitational well so deep that expansion simply does not enter the accounting. And the local group, our bound cluster of galaxies, is held as a unit by the combined gravity of everything in it, firmly enough that the expansion of the universe, for all its eventual dominion over the empty spaces between clusters, has no purchase inside it at all. This is why we can say, with real confidence, that your body is not expanding, the Earth is not expanding, the solar system is not expanding, the galaxy is not expanding, and the local group is not expanding. It is not that these things are expanding a tiny bit, and we cannot measure it. It is that they are not expanding, full stop, because in every one of them a binding force is present that is so much stronger than the expansion, that the expansion is, for practical purposes and for actual physics, switched entirely off. Expansion only does its work where there is nothing to oppose it, in the enormous, almost perfectly empty gulfs between galaxy clusters, where matter is spread so impossibly thin that gravity has nothing substantial to grip, and the gentle, ceaseless stretching of space has the field entirely to itself. Out there, with no bond to overcome, the expansion runs free, and there it is, utterly in charge. The universe, then, is divided cleanly into two kinds of place. There are the bound islands, where binding rules absolutely and expansion is irrelevant. And there are the empty gulfs, where expansion rules absolutely and there is nothing to bind. There is almost no middle ground. And that clean division is the entire reason the deep future takes the specific shape it does, intact survivors adrift in widening emptiness, rather than a universe smeared uniformly thin. Part 7. The Island That Survives. Let us look closely, then, at the island that survives, because it is our island, and its future is more specific and more strange than you might expect. Right now, the local group is not a single thing. It is a loose association, dominated by two great spirals, the Milky Way and Andromeda, separated by about 2.5 million light-years of space, with the smaller Triangulum galaxy nearby, and dozens of dwarf galaxies scattered among them. They are bound together by gravity, which means, as we have seen, that the expansion of the universe cannot pull them apart. But being bound by gravity does not mean staying still relative to one another. Gravity pulls inward, and, over cosmic time, gravity does to the local group what it does to any bound system. It draws the pieces together. Andromeda and the Milky Way are approaching each other. For a long time, astronomers expected a definite head-on collision and merger, with classic estimates, such as the modelling by Cox and Loeb in 2008, placing a major encounter around 4.5 billion years from now. More recent work, using precise measurements of Andromeda's sideways motion from the Gaia Space Observatory, has actually softened that certainty, suggesting the merger is closer to a coin flip over the next 10 billion years rather than a sure thing on a fixed date. But the long-term direction of travel is not really in doubt. A bound group of galaxies, given enough time, merges. The dwarf galaxies fall in. The great spirals eventually meet, pass through each other, are pulled back, and over a vast span of time settle into a single combined galaxy, an enormous elliptical ball of stars, sometimes nicknamed Milkomeda. So here is the fate of our island, stated plainly. The local group becomes one galaxy, a single, vast, merged elliptical galaxy the combined stars of the Milky Way and Andromeda, and all their companions, gathered into one structure. That galaxy is bound. The expansion cannot touch it. It will sit there intact, holding its stars, for a length of time that makes the current age of the universe look like an eye blink. And around it, nothing. That is the picture we have to hold. One galaxy, whole and surviving, and beyond it the empty dark, because every other galaxy has crossed the horizon. The island endures, but it endures alone. It becomes, in the most literal possible sense, an island universe, a single inhabited structure with no other structure anywhere in its reachable cosmos. When we first encountered, in the last part, the fact that bound systems survive the expansion, it sounded like good news, and in a narrow sense, it is. Our galaxy will not be shredded. But look at what survival actually consists of here. The reward for being a bound, intact island is to be the last lit house in a valley gone dark, and then to watch the valley itself recede until even the memory of other houses becomes unprovable. Because that is the next turn, and it is the heaviest one. It is not only that the future Milkomeda will be alone, it is that a thinking being living in that future galaxy, looking out, doing careful and honest science, would have no way of knowing that anything else had ever been there. The expansion does not just isolate the island. It erases the evidence that the island was ever part of something larger. And to understand how complete that erasure is, we need to return to the thing driving all of it, the engine in the basement of the universe, the 68% of everything that we have named and measured and still cannot explain. There is a quiet irony in the fate of our island that is worth drawing out, because it changes how the word survival should feel. When the Milky Way and Andromeda finish their long, slow merger and settle into the single elliptical galaxy we have been calling Milkomeda, that galaxy will, in one sense, be a triumph of permanence. It will be bound. It will be stable. Its stars will wheel around their common center for an almost unimaginable span of time, far longer than the current age of the universe. Expansion will never touch it. Of all the things in the cosmos, a bound galaxy in the deep future is among the most durable. It endures. But endurance and richness are not the same thing, and this is the irony. The galaxy survives the expansion precisely by being cut off from it. The same gravitational binding that protects Milkomeda from being stretched apart is what seals it into its isolation. There is no version of the future in which our galaxy both survives and stays connected. The survival and the isolation are the same fact, viewed from two sides. To be the island that lasts is to be the island that is alone. And think about what that island actually loses, beyond company. It loses the sky, not its own stars, those remain, but the deep sky, the sky of other galaxies, the sky that for us is a window onto the entire rest of creation. A being standing on a world in Milkomeda, 100 billion years from now, will have a night sky. It will be full of the stars of their own galaxy, and those stars will be beautiful, and they will have their own constellations and their own law. But when that being looks between the stars, into the spaces where we, tonight, see the faint glow of 1,000 other galaxies, they will see nothing. The between, the stars dark, for them, will be truly and totally dark. Their universe will appear to end at the edge of their own galaxy. We should be honest that there is loss in that, real loss, even though there is no catastrophe. Nobody is harmed. No civilization is destroyed by the emptying of the sky. The stars of Milkomeda will go on shining, planets will go on orbiting, and if there are minds there, they will go on thinking. The loss is subtler than destruction. It is the loss of the view. It is the loss of context. It is the loss of the ability to look up and see that you are part of something larger, because by then you will not be part of something larger in any way you could detect. The island survives, But it survives as the whole of its inhabitants' knowable world, and a world with no visible outside is a smaller thing to live in than the world we have tonight, even if not one star of it has gone out. Part 8. The engine we cannot name. We have been describing the consequences of dark energy for several parts now: the accelerating expansion, the shrinking horizon, the emptying sky. It is time to look directly at dark energy itself, and to be honest about how strange our relationship with it is. Because dark energy is, simultaneously, the most important thing in the universe, and the thing we understand least, it is the engine driving the entire fate we have been describing, and we cannot say what it is. Start with what we can say. Dark energy behaves like an energy that belongs to space itself. Not to the matter in space, not to the radiation crossing it, but to the empty volume. Every cubic meter of vacuum, on this picture, carries a small, fixed amount of energy simply by virtue of being a cubic meter of vacuum. And this vacuum energy has a peculiar property. Unlike matter, which thins out as space expands, the energy of the vacuum does not thin out. As space expands and there is more vacuum, there is proportionally more vacuum energy, keeping the same density everywhere, always. That property is the whole story of the accelerating universe. As the cosmos expands, matter spreads thinner and its gravity weakens, but the vacuum energy holds its density steady, and so its outward push becomes more and more dominant. The more space there is, the more this energy there is, and the harder the expansion is driven. It is a runaway. The expansion creates more space, the new space carries more dark energy, the dark energy drives more expansion. That feedback is the acceleration. This idea, an energy intrinsic to empty space, has a name, and it is a name we met at the very start of this video. It is the cosmological constant, the very term Einstein added to his equations in 1917 to hold the universe still, and then discarded as his greatest blunder. It turns out Einstein's instinct that such a term could exist was correct. He was only wrong about its value and its job. He wanted it to balance gravity and freeze the cosmos. Its real role is the opposite. It drives the cosmos apart, faster and faster, forever. So far, this sounds like understanding. We have a name, the cosmological constant, and a behavior, a fixed energy density of the vacuum, and a consequence, accelerating expansion. But now we come to the part that should genuinely unsettle anyone who takes physics seriously. Because when we try to calculate how much energy empty space should have, we get one of the most spectacular failures in the history of science. Our best theory of the small-scale world, quantum field theory, tells us that empty space is not truly empty. The vacuum seethes with quantum activity, fields fluctuating, particle pairs flickering in and out of existence. All that activity should carry energy, and that energy should be exactly the kind of vacuum energy that drives cosmic acceleration, so physicists can calculate it. They can estimate how much energy the vacuum ought to have, according to quantum theory. The answer they get is too large, not too large by a little, not too large by a factor of 10, or 1,000, or 1,000,000. The theoretical prediction for the energy of empty space exceeds the value we actually measure from cosmic expansion by something on the order of 120 orders of magnitude. That is a 1 followed by 120 zeros. The prediction and the observation disagree by a factor so vast that there is no real way to picture it. It is routinely called the worst quantitative prediction in the history of physics. To feel the size of that failure, imagine trying to estimate the number of grains of sand on a single beach and arriving at an answer larger than the number of atoms in the entire observable universe. That is not a small error to be tidied up later. It is a sign that something fundamental about empty space and about the energy it carries is missing from our deepest theory. Sit with what that means. The thing that makes up 68% of the universe, the the thing driving the entire future we have been describing, the engine carrying every distant galaxy beyond our horizon, is something for which our deepest theory gives an answer that is wrong by a factor of 10 to the 120th power. We can measure dark energy. We can chart its effects with great precision. We can predict, from those measurements, the emptying of the sky and the isolation of our galaxy. But we cannot derive it. We cannot explain why it has the value it has. We do not know what it is. This is the disquieting truth at the core of the matter. The fate of the universe is being written by a hand we cannot see and cannot name. Every confident statement about the deep future, the 100 billion years, the empty sky, the surviving island, all of it rests on the behavior of a quantity that physics, by its own admission, does not understand. We are forecasting the end of the cosmos using an engine whose blueprint we have never been able to read. And it gets worse, or at least more uncertain, because so far we have been assuming that dark energy is a true constant, that the energy of the vacuum has one fixed value and always will. That assumption is built into the standard model of cosmology. It is the simplest possibility. But in the last couple of years, a major experiment has begun to suggest, very tentatively, that the assumption might be wrong. And if it is wrong, then the ending of the universe is not even settled. It is still, genuinely, up for grabs. It is worth dwelling on just how unusual dark energy is as a substance, because part of what makes it so hard to explain is that it does not behave like anything else in the cosmic inventory. Think about ordinary matter, the stuff of stars and planets and people. When space expands, ordinary matter thins out. The same amount of matter is now spread through a larger volume, so its density drops. Double the volume, halve the density. That is intuitive. It is what we expect of stuff. Radiation, the light crossing the universe, thins out even faster, because expansion not only spreads it through more volume, but also stretches its wavelength and saps its energy. So both matter and radiation become more dilute as the universe grows. The universe, in its matter and its light, is becoming gradually emptier and fainter just by getting bigger. Dark energy does none of that. As space expands, the density of dark energy stays the same. Make twice as much volume, and you have twice as much dark energy at the identical density it had before. It is as if every new cubic meter of space comes into being already filled with its own fixed ration of this energy. The vacuum is not a container that dark energy sits in and gets diluted within. The vacuum, apparently, is the dark energy, or carries it inseparably, so that more vacuum simply means more of it. That single peculiar property is the key to the entire runaway future. Because matter dilutes and dark energy does not, the early universe was dominated by matter, when everything was packed close and gravity was strong. But as expansion thinned the matter out, there came a turning point, a few billion years ago, where the unchanging dark energy overtook the dwindling matter and became the dominant influence. From that turning point onward, the universe was committed. The more it expanded, the more dark energy there was, in total, to drive the expansion, while the matter that might have resisted grew ever more dilute and feeble. It is a process that, once it tips over, only deepens. Expansion begets space. Space begets dark energy. Dark energy begets expansion. We are living after the tipping point. The runaway has already begun. And here is the thing that should genuinely keep a thoughtful person up at night. A substance whose density never dilutes, that appears with every new parcel of space, that grows in total without limit as the universe grows, is a substance with no precedent and, currently, no explanation. We did not predict it. We cannot derive its value. We have one theoretical estimate of what the energy of the vacuum should be from quantum field theory, and as we are about to see in detail, that estimate is not slightly wrong. It is wrong by the largest margin any prediction in the history of science has ever been wrong. The engine driving the fate of everything is not just unexplained. It is, at the level of our deepest theory, actively, spectacularly mysterious. Part 9. The constant that might not be constant. The whole picture we have built rests on a single, quiet assumption. We have been assuming that dark energy is a true constant, that the energy of empty space has one value, the same yesterday, today, and 100 billion years from now. That assumption has a name, the cosmological constant model, and for the past 25 years it has been the standard, default description of the universe. It is the simplest possibility, and the simplest possibility is usually the right place to start. But simple and correct are not the same thing, and over the last couple of years a major experiment has begun, very gently, to suggest that this particular simple assumption might not hold. The experiment is called the Dark Energy Spectroscopic Instrument, usually shortened to DESI. It is a remarkable machine, mounted on a telescope in Arizona, designed to do one thing on a scale never attempted before. It measures the precise three-dimensional positions of millions upon millions of galaxies, building the largest map of the universe ever made. And the reason a map of galaxy positions can tell you about dark energy is one of the most elegant ideas in modern cosmology. In the very early universe, before there were galaxies, the cosmos was a hot plasma, and through that plasma traveled pressure waves, essentially sound waves, sloshing outward from every clump of matter. When the universe cooled enough for the plasma to become transparent, those waves froze in place, leaving a faint but real preferred distance scale stamped into the distribution of matter. Galaxies are very slightly more likely to be found separated by that particular distance, about 500 million light-years, than by any other. Cosmologists call this scale the baryon acoustic oscillation, and the important thing about it is that we know its true size. It is a ruler of known length, laid down by the early universe and printed across the whole sky. When DESI maps galaxies near and far, it is measuring how big that ruler appears at different distances, which is the same as measuring how much the universe had expanded at different points in cosmic history. In effect, DESI is reading the expansion history of the universe directly off the arrangement of galaxies. And in its data releases in 2024 and 2025, combining its galaxy map with measurements of the cosmic microwave background and with supernovae, DESI found something that made cosmologists sit up. The data showed a preference, a statistical hint, for a dark energy that is not constant. A dark energy that appears to have been somewhat stronger in the past and to be weakening as time goes on. The strength of that hint depends on exactly which data sets you combine, and it falls somewhere in the range of 2.5 to roughly 4 on the scale physicists use to measure confidence. That is interesting. That is worth paying very close attention to. But it is not yet certain. In physics, a result is not considered a discovery until it reaches a much higher bar, and the DESI hint has not reached it. It might strengthen into a genuine revolution as more data arrives. It might also fade away, as tantalizing hints sometimes do. But consider what is actually at stake in that hint, because this is the point. Whether dark energy is constant or changing decides what kind of ending the universe gets. Stand at a fork in the road. Down one path, the DESI hint holds up, and dark energy is weakening. If dark energy fades over cosmic time, then the accelerating expansion eases. The cosmic event horizon stops drawing inward so aggressively, perhaps stops shrinking altogether. The emptying of the sky slows down. The future becomes a little less isolated, a little more connected than the standard grim forecast. Of all the paths, this is the gentlest. Down the other path lies something far worse. If dark energy is not weakening but strengthening, growing more powerful as the universe ages, it crosses into a regime physicists call phantom energy. And phantom energy does not merely isolate the islands, it eventually destroys them. A phantom dark energy, its density climbing without limit, would in a finite time grow strong enough to overpower even the bonds we said were safe. It would, in its final stages, pull apart galaxy clusters, then individual galaxies, then solar systems, then planets, and in the last fraction of a second, it would tear apart atoms themselves. Physicists call this scenario the Big Rip, and it was worked out in detail in a 2003 paper by Caldwell, Kamiankowski, and Weinberg. In a Big Rip universe, the comforting fact that bound systems survive expansion is only temporarily true. Eventually, expansion wins everywhere, all the way down. So picture yourself standing at that fork, looking down both roads. One road leads to a slightly warmer, slightly more connected future. The other road leads to a cosmos that comes apart in every joint, atoms and all. And the disturbing truth is not that we know which road we are on. The disturbing truth is that we do not. The fate of everything that exists hangs on whether a single number, the dark energy equation of state, sits exactly at the constant value, or just above it, or just below it. And right now, standing here in the early 21st century with the best instruments we have ever built, we cannot yet tell you which. We will get better data. Deci continues. Other surveys are coming. Within our lifetimes, we may know which road the universe is on. But tonight, the honest scientific position is the most unsettling one of all. The universe has an ending, and we do not yet know what it is. And the difference between a gentle ending and a violent one comes down to a number we have not finished measuring. Let us walk a few real steps down each of the two roads at the fork, because both fates deserve to be felt, not just named. Take the gentler road first, the one where dark energy is weakening. Walk down it. The acceleration eases off over cosmic time. The cosmic event horizon, instead of drawing relentlessly inward, slows its retreat, and the emptying of the sky becomes a slower, less complete process than the standard forecast. More galaxies stay within reach for longer. The deep future on this road is still quiet and still cold and still vast, but it is a shade less lonely. A future astronomer might still have a few distant smudges of light to study. The window of legibility we will talk about later stays open a little wider, a little longer. It is not a happy ending, exactly, but it is the least sealed of the possible endings, and after everything this video has described, a future that is merely very isolated rather than absolutely isolated counts, almost as mercy. Now, go back to the fork and walk the other road, the phantom road, the one where dark energy grows stronger with time. The first stretch of this road looks like the standard future, the sky emptying, the islands isolating. But then it keeps going, past where the standard road stops. The dark energy density, instead of holding steady, climbs. And as it climbs, the bonds we called safe stop being safe, one tier at a time, from the largest scales down. First, the great clusters of galaxies, already loosely bound, are pulled apart. Then, as the density climbs further, individual galaxies begin to come undone, their stars no longer able to hold a common orbit. Then solar systems unbind, planets drifting free of their suns. Then, in the final stretch, the road grows truly terrible, because the climbing dark energy reaches the strength of planetary gravity, and worlds themselves come apart. And then in the last instance, it reaches the strength of the electromagnetic bonds inside matter, and atoms are pulled to pieces. That is the Big Rip, the road's end. And on this road, the comforting fact that bound systems survive expansion was only ever a statement about the early part of the journey. Now, step back from both roads and stand again at the fork itself, because the fork is where physics actually is tonight. We do not get to choose the road, and we do not yet know which one we are on. The whole of it, the gentle fade or the universal tearing, hangs on the behavior of the dark energy equation of state, on whether one number sits exactly at its constant value, or a hair above it, or a hair below. The DESI hints have nudged our attention toward the possibility that the number is not simply constant, but they have not told us, with the confidence physics demands, which way it leans. We are standing at the fork, in the dark, with a hint of a breeze down one path, unable yet to say where either path truly goes. That uncertainty is not a failure of this video to give you an answer. It is the answer. The ending of the universe is, at this moment in the history of science, genuinely unknown, and we are the generation alive while the measurement is still being taken. Part 10. The escape hatches that don't open. By now, this video has painted a future that is difficult to sit with. An emptying sky, an isolated island, an engine we cannot explain, and an ending we cannot yet pin down. It would be only natural, hearing all of this, to look for a way out, to hope that somewhere in the argument there is a loose thread, a mistake, an escape hatch. And it is worth taking that hope seriously, because there are, in fact, alternative ideas out there, ideas that would make the disturbing conclusion go away. We should look at them honestly. We should also be honest about whether they hold. The first escape hatch is the oldest one, and it is the most appealing, because if it were true, the entire unsettling future would simply evaporate. The idea is this: what if the universe is not really expanding at all? What if the redshift of distant galaxies, the very observation that started all of this, has some other cause? This idea has a name. It is called tired light, and it was first floated by the astronomer Fritz Zwicky back in 1929, the same year Hubble published his law. The suggestion is that light simply loses energy as it travels across enormous cosmic distances, growing redder not because space is stretching, but because the light itself is, in some sense, getting tired. If that were true, the galaxies would not be receding at all. The universe would not be expanding. There would be no accelerating fate, no shrinking horizon, no emptying sky. The disturbing truth would dissolve. It is a lovely thought. The trouble is that it is wrong, and we can show that it is wrong because the universe gives us several independent ways to check. Consider distant supernovae again, those standard candle explosions. An explosion has a natural duration, a characteristic time over which it brightens and fades. If the universe is expanding, then the light from a distant explosion should arrive stretched out in time, as well as in wavelength, so the explosion should appear to unfold in slow motion. And that is exactly what we see. Distant supernovae are observed to fade in slow motion by precisely the factor that expansion predicts. Tired light predicts no such slowing. Tired light fails this test outright. It fails others too. It cannot reproduce the near-perfect shape of the cosmic microwave background spectrum. It does not match the consistency of the baryon acoustic oscillation measurements we discussed in the last part. The universe has handed us test after test, and expansion passes every one, and tired light fails them. The first escape hatch is painted on the wall. It does not open. The second escape hatch is more sophisticated, and it deserves more respect. The idea here is that maybe dark energy is not real at all. Maybe we have simply misjudged our own situation. Suppose that we happen to live near the center of an unusually empty region of the universe, a vast bubble where galaxies are more thinly spread than average. In such a region, the expansion would behave a little differently than it does elsewhere, and an observer in the middle might be fooled into thinking the universe was accelerating when really they were just sitting in an unusual spot. There is genuine science here. Large underdense regions do exist, and they are studied seriously, and our own corner of the universe does appear to be somewhat underdense. But for this idea to do away with dark energy completely, the void we live in would have to be extraordinarily large, and we would have to sit improbably close to its exact center. That runs against one of the deepest and best-tested principles in cosmology, the principle that we do not occupy a special place, that our location is not privileged. To replace dark energy with a void is to claim that we happen to live, by sheer luck, at the bullseye of one of the largest empty regions in existence. Most cosmologists regard that as far harder to swallow than dark energy itself. The void cannot do the job alone. The second escape hatch, examined closely, does not open either. And then there is a third reaction, not really a scientific theory, but a suspicion, and it is worth addressing because it is common. The reaction goes like this. The conclusions are so bleak, an emptying sky, a forgotten origin, that surely someone must be hiding the truth, softening it, keeping the real picture from the public. But here the facts run exactly the other way. The most isolating result in all of modern cosmology, the End of Cosmology paper by Krauss and Scherer, was not buried. It was published openly in the scientific literature with a title that announced its own bleakness, and it has been discussed and taught and built upon ever since. Cosmologists did not hide the disturbing truth about the expansion of the universe. They printed it and put it on the shelf in plain sight for anyone willing to read it. The discomfort is real, but it was never concealed. It has simply been waiting, in the open, for anyone willing to follow the data all the way to the end. So the escape hatches do not open, none of them. The redshift is real, the expansion is real, dark energy is real, and the future we have described is the one the evidence actually points to. There is no comforting wrong answer to retreat into. There is only the truth, and the question of what we do with it. And to answer that, we have to follow this all the way to its furthest consequence, the one that is less about physics than about something stranger. What it will mean, in the deep future, to look up at the sky and not be able to read it anymore. There is a fourth reaction worth addressing, gentler than the suspicion of a cover-up but just as common, and it is the hope that the universe has a way of starting over. If the deep future is an empty, isolated cold, perhaps that is not truly the end. Perhaps the story loops. Perhaps the end of one cosmic era is the seed of the next. This is not a fringe hope. There are serious, carefully constructed theories along these lines, proposed by respected physicists. There are cyclic models in which the universe passes through endless rounds of expansion. There is a proposal called conformal cyclic cosmology, developed by Roger Penrose, in which the cold, empty, far future of our universe is, by a deep geometric reinterpretation, identical to the hot, dense beginning of a new one, so that the dark era is not an ending but a doorway. There are bounce models in which a contracting phase rebounds into a new expansion. These ideas are real physics, and the channel takes them seriously, and they offer a genuine thread of consolation, the possibility that what looks like a final silence is actually a handoff. But honesty requires us to place them correctly. These cyclic and bounce models are minority positions. They are not the consensus. They are not what the bulk of the evidence currently points to. The mainstream picture, the one supported by the data we actually have, remains the slow fade, the heat death, the long cold quiet. The cyclic models are possibilities held open, not conclusions reached. So if you take comfort from them, take it as you would take comfort from a door that might be there, in a wall you cannot yet see clearly, rather than from a door you have already found and opened. The hope is permitted. It is simply not yet knowledge. And notice that even the cyclic models do not rescue the particular thing this video is most concerned with. Even if the universe as a whole loops, even if a new era follows the cold dark of ours, that does not reconnect our galaxy with the galaxies that have crossed our horizon. It does not restore the view. It does not give the future astronomer in Milkomeda back their evidence of the Big Bang. Whatever happens to the universe on the grandest scale, the local story, the story of our island and its lost sky, runs the same way. The disturbing truth about the expansion of the universe is robust. It survives even the most hopeful of the grand cosmological scenarios. The escape hatches, examined one by one, in good faith, simply do not open onto a different local future. Which means there is nothing left to do but follow this all the way to its end and look directly at the strangest consequence of all. Part 11. The Universe That Forgets. We come now to the heaviest part of this story, and it is not a fact about galaxies, or horizons, or energy. It is a fact about knowledge, about what can be known, and for how long, and by whom. Everything we understand about the universe, its age, its expansion, its beginning, we learned by looking at the sky, and not the nearby sky. We learnt it by looking at the distant sky, the sky beyond our own galaxy. The expansion of the universe was discovered by measuring the redshifts of other galaxies. The Big Bang was confirmed by detecting the cosmic microwave background, the faint afterglow of the hot early universe, which still bathes the whole sky in a whisper of microwave light. The proportions of dark energy and dark matter and ordinary matter were measured by reading the patterns in that ancient light and in the arrangement of galaxies across cosmic distances. Every major fact about the origin and nature of the universe came from observing things far outside the Milky Way. Now hold that thought against everything we have established tonight. In the deep future, in roughly 100 billion years, all of those distant galaxies will have crossed the cosmic event horizon. They will be gone from the observable sky, and the cosmic microwave background, that crucial afterglow, will not survive either. Expansion stretches its light too, redshifting it further and further toward longer and longer wavelengths, dimmer and dimmer, until it is stretched beyond any conceivable detection. The afterglow of creation will be stretched into silence. So let us go there. Let us stand, in imagination, inside that far future, 100 billion years from now, on a world somewhere in Milkomeda, the great merged galaxy that our local group will have become. And let us watch an astronomer of that era at work. This astronomer is not primitive. Picture a thinking being, deeply curious, scientifically careful, equipped with the finest telescope their civilization has ever built, an instrument far beyond anything we possess. They point it at the night sky, and they study what they see, and they do everything right. They are rigorous, they are honest, they follow the evidence, and here is what their evidence shows them. They see their own galaxy, Milkomeda, full of stars, wheeling slowly, rich and complex, and they see, beyond it, nothing, no other galaxies, no faint smudges of distant light, no background glow of microwaves. They point their magnificent telescope into the dark between the stars, and they find only dark, perfect and featureless, in every direction, all the way down to the limits of their instrument and past them. What conclusion will this careful, honest astronomer reach? They will conclude, from the evidence in front of them, that the universe consists of a single galaxy, their galaxy, surrounded by infinite empty space. They will see no expansion because there will be nothing external left whose recession they could measure. They will find no afterglow because it will have faded beyond all detection. They will have no reason whatsoever to suspect a Big Bang, because every shred of evidence for it will have left the observable sky. Their best, most rigorous science will tell them that they live in a single, static, eternal island, and that it has always been so, and they will be wrong, completely wrong, and there will be no possible way for them to know it. This is the disturbing truth about the expansion of the universe, in its final and fullest form. It is not merely that the universe empties. It is that the universe erases the evidence of its own history. The expansion does not just carry the galaxies away, it carries away the proof that the galaxies were ever there. It carries away the proof that the universe had a beginning. 100 billion years from now, The Big Bang will not be a forgotten theory. It will be an unprovable one. The single most important fact about the universe, that it began, that it has been expanding for billions of years, will have become, for any future observer, permanently unknowable. Think back to the Valley of Houses, the lights going out one by one. We watched, from our hillside, the windows go dark across the valley. But the future astronomer in Milkomeda does not watch the lights go out. They are born long after the valley is already black. They have never seen a single distant light in their entire existence. They do not know the valley is there. They cannot even know that there was ever anything to see. Nobody hid this truth from them. That is the strangest and quietest part. There is no conspiracy, no cover-up, no deception. The truth simply, gently left the room. It receded across the horizon at the speed of stretching space, and it took the evidence with it, and it left behind a sky that lies by omission to anyone who looks. Knowledge, it turns out, is not permanent. On a long enough timescale, even the truth about the universe itself has an expiration date. The universe forgets, and it ensures, by the very process of its expansion, that its inhabitants forget along with it. Let us stay inside the far future observatory a little longer, because there is something here that deserves to be felt slowly, and it is not horror. It is closer to a kind of vertigo. The astronomer of Milkomeda is not a fool. Set aside any image of a primitive stargazer. Picture instead the finest scientist that civilization will ever produce, with instruments and mathematics and patience far beyond ours, doing science exactly as science should be done. They form hypotheses. They test them against observation. They discard the ideas the evidence does not support and keep the ones it does. They are, by every standard we could name, doing it right. And doing it right leads them, inexorably, to a false conclusion. They observe a single galaxy in an unbroken dark. They observe no recession, because there is nothing external left to recede. They observe no afterglow, because the afterglow has been stretched into undetectability. Every measurement they can make is consistent with a static, eternal, single galaxy universe, and inconsistent with nothing. The hypothesis that the universe is static and eternal is not, for them, a failure of imagination. It is the hypothesis the evidence supports. A Big Bang, an expansion, a vanished sky of 1 trillion other galaxies, all of that would be, to them, an extravagant story with not one shred of observational support. A good scientist of that era would set it aside, exactly as a good scientist of our era sets aside claims with no evidence behind them. This is the vertigo. It is not that the future astronomer will be ignorant. It is that they will be rigorous and careful and honest and wrong, and that their rigor will be the very thing that locks them into the error. The universe will not have lied to them, exactly. It will have done something subtler. It will have removed the evidence so completely that the false picture becomes the one that good method endorses. Truth, in that era, will not be hidden behind bad reasoning. It will be hidden behind the horizon, where no reasoning, however good, can reach. And now let the vertigo turn around and point back at us, because it should. If a future civilization can be rigorous and wrong because the evidence has left their sky, then we are forced to ask the uncomfortable question about our own sky. We have been assuming, all through this video, that we are the lucky ones, the observers who came early enough to see the evidence intact, and in large part we are. But the horizon is not only a future event, the horizon is here, now, around us, and it has been here, doing its work, for billions of years already, which means the honest, unsettling possibility is that we, too, are missing pages. That there were things, once, within reach, that crossed our horizon before any human looked up. That our own rigorous, careful, honest cosmology is built on the evidence that happens to remain, and that we have no way of knowing what evidence is already gone. The future astronomer is not only a cautionary tale about them, they are a mirror held up to us. Consider one more time what it would actually be like to be that future astronomer, and to be told the truth. Imagine you could send a message across 100 billion years and place into their hands the complete, correct history of the cosmos, the Big Bang, the hot, dense beginning, the trillion galaxies that once filled their sky, the long, slow recession that carried every one of them away. You hand them this history, and it is true. Every word of it. They would have no way to confirm a single line. Not because they lack intelligence, and not because they lack instruments, but because confirmation requires evidence, and the evidence would lie permanently beyond their horizon. The history you handed them would be, to them, indistinguishable from a myth. A beautiful story, perhaps, but one with no observable support, the kind of claim a careful thinker is trained to set gently aside. The truth would be in their hands, and they would, correctly by their own standards, decline to believe it. That is the deepest and quietest part of the disturbing truth. It is not only that the universe forgets, it is that the universe arranges things so that, in the deep future, the truth and a baseless story become impossible to tell apart. Knowledge does not simply fade. It loses the very thing that makes it knowledge rather than guesswork, which is the ability to be checked against the world. 100 billion years from now, the origin of the universe will not be a secret being kept. It will be a fact that has lost its evidence, and a fact without evidence, however true, is something a rigorous mind cannot hold. The universe will not have hidden its history. It will have done something stranger and more final. It will have made its own history unprovable, and it will have done it not through any act of concealment, but simply by continuing patiently to expand. Part 12. The lit window we live in. We have followed the expansion of the universe all the way to its end, and what we found there was not an explosion and not a collapse, but something quieter and stranger, a universe that empties itself, isolates its survivors, and erases the record of its own beginning. That is a heavy place to arrive. So before we finish, let us turn around and look back at where we are standing, because the view from here, once you understand the whole journey, is not only bleak, it is also something else, something close to a privilege. Consider the position we are actually in tonight. We exist early. The universe is 13.8 billion years old, and the deep future we have been describing, the emptying sky, the isolated galaxy, the forgotten origin, lies 100 billion years and more ahead. We are not living in the long, dark, forgetful era of cosmic history. We are living near the bright beginning of it, in a narrow, early window when the universe is still young enough and still full enough to be legible. The distant galaxies have not yet crossed the horizon. The cosmic microwave background still bathes our sky, still carrying its readable pattern. The evidence is all still here. The sky above us tonight is a document, and it still has its text intact, and we happen to have arrived in time to read it. That future astronomer in Milkomeda, careful and honest and wrong, will never have what we have. They will look up into an empty dark and find no clue to where they came from. But we look up and we find the whole story written overhead. We can see the other galaxies. We can detect the afterglow of the hot early universe. We can measure the expansion, chart its acceleration, and reconstruct 13 billion years of cosmic history. Because the universe, right now, in our era, is still showing its work. Of all the moments in which a curious mind could have opened its eyes, we opened ours during the one stretch of cosmic time when the universe can still be understood by looking at it. That is not a small thing. The same physics that dooms the far future to forgetfulness has handed our particular moment a gift. We are among the observers, perhaps among the last observers for a very long span of cosmic time, who can still know where the universe came from. The window is open now. It will not always be. And we are here while it is. So what should we do with that? Mostly, I think, we should look. We should pay attention to the sky while it still has its story to tell. There is something clarifying in understanding that the view is temporary, that the richness overhead is not a permanent fixture, but a passing condition, that the galaxies scattered across the dark are, in the slowest possible motion, leaving. It makes the sky we have feel less like furniture and more like a guest. The universe is not obligated to be legible. For this brief stretch, it is. That is worth not taking for granted. And we should end, as this channel always tries to, not with a tidy answer, but with the open question. Because the open question here is the most haunting part of all. We have said that in the deep future, the evidence of the universe's history will recede beyond the horizon. We have said that a future civilization will look up and find a sky that has been emptied of its past. But here is the thought to carry away with you tonight. If the expansion of the universe can carry evidence beyond the horizon, then it has already been doing so for billions of years, since long before we existed. The horizon is not a future event. It is here now, around us, all the time. And that means there may already be things, structures, regions, whole chapters of the cosmic story that have already crossed beyond our reach, that were already gone before we ever looked up. We tend to assume that the observable universe is the universe. But the observable universe is only the part that has not yet been carried away. We are not seeing everything, we are seeing what is left. So the universe is not only forgetting its future, it has a past it has already forgotten, and so do we, and we will never know what was in it. The sky tonight is still a document we can read. But it is a document with pages already missing, pages that drifted beyond the horizon before there was anyone here to turn them. And the quiet, disturbing, genuinely open question, the one to lie awake with, is simply this: what was written on them? Let us hold, for a last long moment, the strange double feeling this whole journey leaves behind, because the channel does not want to send you off with only the cold of it. On one side, there is the genuine weight of what we have described. The universe empties. The sky we love is temporary. Our galaxy survives only by being sealed into solitude. The evidence of the cosmos's own birth will, in the deep future, recede beyond all recovery, and rigorous minds will look up into a dark that quietly misinforms them. None of that is softened by pretending otherwise, and this video has not tried to soften it. It is the disturbing truth about the expansion of the universe, and it is true, but on the other side, set against that weight, is the fact of where and when we are standing. We are not the forgetful ones. We are not the astronomer in the empty observatory. We are the observers who arrived during the lit window, while the document of the sky is still legible, while the other galaxies are still there to be seen, and the afterglow of the beginning still washes faintly over the whole sky. We can know where the universe came from. We can trace its expansion. We can stand on a small planet and reconstruct 13.8 billion years of cosmic history, because the universe, in our era, is still showing its work. That capacity is not guaranteed to observers. It is not permanent. It is a property of this particular, early, bright stretch of cosmic time, and we are inside that stretch. There is a way of holding both of those at once, and it is, I think, the right way to end. The temporariness is exactly what makes the view precious. A sky that lasted forever, that could always be read by anyone at any time, would be a kind of furniture, taken for granted, never really seen. A sky that is legible only for a while, only early, only to the lucky, is something else. It is a rare thing, briefly available, and we happen to be the ones it is available to. That should not make us mournful so much as attentive. The right response to a temporary marvel is not grief that it will end. It is to actually look at it while it is here. So, when this is over, sometime tonight or another night, step outside if you can, And look up. The galaxies you cannot see with your eyes are still out there, and the ones our telescopes can reach are still within reach, and the faint glow of the universe's first light still surrounds you on every side. Undetectable to your senses, but real and present and readable by the instruments our species has built. You are looking at a document that will not always be legible during the window in which it still is. That is the gift folded inside the disturbing truth. The universe is expanding, and it is carrying its history away, and it has not finished carrying it yet, and we are here, now, in time to read it. And the open question, the one to carry into sleep, is the gentle and haunting one we arrived at a moment ago. The universe has been carrying things beyond the horizon since long before we existed. So there are pages already gone, chapters of the cosmic story that crossed out of reach before any eye on Earth turned upward. We will never know what they held. We are reading a book with its opening pages already lost to the dark, and doing our patient best with what remains. The sky tonight is still a document we can read. But it is not the whole document. It never was. And what was written on the pages the universe has already carried away, we will, quietly and forever, never know.